We have a cubic function, okay? The cubic function is x cubed minus 5x squared plus 3x plus 5. Now, what we know in the past is this, that usually it either goes this way or it will go this way here, something like that, one or the other, okay? I usually identify that by just putting in the calculator and figuring out which one's which. What's a positive x cubed, what's a negative x cubed. I don't have it learnt off because I use the calculator function to figure out what shape they are. Okay. Now, the thing is, we're sort of segmenting it. See the way it's 0 to 5? So it's like we're taking a chop of each one. And I don't know if both turning points are in this sample or not. So I could be down the very bottom. My sample could be like this, in between these two parts here. And you can see there's no turning points. So turning points aren't guaranteed, is what I'm trying to say. So when you see maximum and minimum values, what's the difference between maximum and minimum values and maximum and minimum points?
The x value with the y value.
The maximum and minimum refers to the y value only. While if you're talking points, it's referring to the x and the y value. As it turns out, you're going to get both of them anyway, but just be specific in your answering, okay? So the usual part comes true, okay? So we say, I don't know why just the endpoints, there's no need for that. Okay, I'm just going to find the maximum and minimum value here, okay? Oh, oh yeah. Okay, so what we're going to do is we're going to enter this into my calculator function anyway, as it turns out. And what I can do is table x cubed minus 5x squared plus 3x plus 5. Start at 0, end at 5. So, step of 1. You can see your first 2 points are 0, 5 and your last point is 520. Happy with that? 0, 5 and 520. Okay, so that's where it starts off and that's where it ends. Now we're going to go through our usual routine of finding the maximum and minimum. Okay, so the maximum and minimum is we differentiate once, so we say y equals x cubed minus 5x squared plus 3x plus 5. We differentiate that and we get 3x squared minus 10x plus 3 equals 0 for turning points. Reference number is 9. 9 breaks up into minus 1 minus 9. So 3x squared minus 1x minus 9x plus 3 equals 0. X into 3x minus 1 minus 3 into 3x minus 1 equals 0. And then what we're going to get is x minus 3 and 3x minus 1 equals 0. Once we did that, we're going to get x equals 3. 3x minus 1 equals 0, x equals 1 over 3. They're the x values, not the y values. We got to plug them back into the original equation. However, I'm feeling pretty lazy, so what I'm going to do is I'm going to, first of all, I'm going to look at the calculator for 3. The answer for 3 is minus 4. I'll take that. Then I'm even going to be lazier because I have that already entered in, so what I'm just going to do is I'm just going to change up the see the way I need a third, right? So what I'm going to do is I'm just going to go to the start. I'm going to put an end of 1. I'm going to do my step as 1 over 3, just to be sly about it. And you can see it's a much quicker way of getting my answer. 5.48. Or just sub in a third and use your calculator normally. Okay? So 5.48. Or 5 and, yeah, we can just do 5.48, it's not a big deal. Okay, you can get that in fraction mode if you sub it normally. So there you go. So the values of f at the endpoints. So the endpoint. So it says 20 is the maximum. So in this solution here, it says 20 is the maximum value. What does it mean by that? 20 is the highest value. So if I was to draw a diagram of what exactly we're looking at, yeah. So guys, what we have here is our turning point of, was it 3 minus 4? That's that part down there, right? We have our maximum value of, what was it, a third and 5.84 or something like that? 5.48. And then you have your, what was it, 520 was up here, which is the point we got at the start. And then your very end point is, sorry, 0.5, okay? Now, says is the values of f at the endpoints of a and the points where f of x equals 0 are, so what it's telling me is that 20 is the maximum value of f on a, alright? They're saying is that the maximum value within this interval is 20 and the minimum value within this interval is minus 4. That's evident from the graph, which is the highest and which is the lowest, yeah? But our definition of maximum and minimum is the turning point, which is 5.48 and minus 4. I would stick to the definition we know, which is the definition we know is that it's the minus 4 and the 5.48. I think the 20 is a mistake. I'll double check that. Okay. All right, guys. Now, next, state whether f is injective. Give a reason for your answer. Now, first of all, what is injective? What does that actually mean? We did it a while ago in the differentiation chapter. Haven't seen it in a long time, I'd say. Now, what an injective function means is that when we're drawing points, an injective function, each input, so if you have a point, let's say 1, 3, 2, 5, 3, 7, see the way they all go to a different y value? It's basically like a line, yeah? And in a curve, you can have two values, two inputs that have the same output. So in a curve, you might see another point 4, 7. So that means when you draw a horizontal line, it hits the graph twice. When any horizontal line hits the graph more than once, it means that it's most definitely not injective. That makes sense? Okay. Now, just while we're here, we'll just talk a bit about surjective as well. Surjective is basically the case of a U-shaped graph. You can see that in a surjective graph, the points 3, the inputs of 3 and 4 give you a value. Let's call it 9 for argument's sake. So the point 3, 9 and 4, 9 both have the same output. This means that they're both on the same height on the graph, which is when you draw a horizontal line through y equals 9, you hit it twice. Hence, surjective function. Okay? Bijective function is a perfect one-to-one match. Now, what we mean by a perfect one-to-one match is that it's surjective in the way that everything in the range or the codomain is used. Okay? You'll see that in an injective function, not every possible output is used. But in a bijective function, every possible output is used. Okay? This means it's a continuous line. If it's not continuous, it means there's a gap in the outputs, which means it's not a, what's that word? It's not a surjective function. Okay, it has to be continuous all the way across. Okay? Now, what we're asked, what this question is, state whether f is injective. Now, it is injective. Sorry, is it? It's not injective, is it? Sorry, 1 second. Okay, f is not injective, and the reason why it's not injective is I can draw a horizontal line that cuts it in more than one spot. 2 spots maximum, isn't it? So this makes the function not injective because there are horizontal lines that exist that cut it in one place only. Now, if I restricted the function to, I don't know, let's say, where's this one end? If I restricted the function in between x greater than 4.5, what happens then? If x is greater than 1.5, look what happens now. All the horizontal lines cut the graph how many times? They cut it once. And this means that it's a one-to-one correspondence, which emphasis on horizontal lines there, okay? This means that it's a one-to-one correspondence, which makes it a bijective function. Okay? So you can see that by restricting your range or restricting your domain, the inputs, you can make it bijective or surjective by just taking a chunk of the graph.
Yes, sir. You could explain why it's injective again. I understood what you did up there.
Injective means that you can't have the same. Injective means, like, if I drew a graph like this, 1, 2, 2, 4, 3, 4, I know straight away this is an injective because 2 and 3 have the same output of 4.
Yeah.
That means that it bends. It has 2 of them at the same level. That means it's automatically not injective. Okay? Yes?
You see in injective C in codomain is not busy.
That's what I said earlier, that not all the values, all the possible y values are used. So when you draw a graph, see the way every y value in existence is going to get used, because it's going all the way up and all the way down. However, if there's some graphs, remember we were talking about the asymptotes earlier, where the y value, there's certain y values that can't be used. Actually, lads, good question there. Remember I was talking about the asymptotes yesterday? There's a certain y value that can't be used in asymptotes. Therefore, this qualifies, it cannot be surjective because not everything is busy. Okay? So what I mean by not busy is that every possible output is not going to be used. While in a injective function, you're allowed to have gaps. It is injective. I'll tell you why. If you consider the black lines the x-y axis, okay, and there's a definite one-to-one correspondence for every horizontal line there. Every horizontal line I draw from this point onwards hits those lines only once. So there's a one-to-one correspondence. However, not every y value gets used, so it doesn't qualify for being bijective anymore. It's only surjective because not every y value gets used.
It's not injective.
It's not. That's just bijective. Sorry. It has. Yeah, you're right. Because in surjective every y value has to be used. That's not the case. So therefore it gets put back down to injective, one-to-one correspondence. You're right. And 2 x values will never have the same y value because you can see in the shape of the graph every x value is either going upwards or downwards. So it won't have the same y value. They'll only ever have the same y value when it bends. Okay? Yep.
Can you give an example of a surjective?
Surjective function would be what we're saying, the one with the asymptote where you have f of x equals, I think we had something like 2x over x plus 2 yesterday. If I drew that function that function is something like this. If you imagine that to be my x, y, oh dear, I'm running out of space here. I'll go to the next page. If you imagine I drew any function that has like a letter on the bottom, like something like that, or something like this. These ones here tend to be have asymptotes. Okay, so they have a horizontal. I need to use a different color here. So you have a horizontal and a vertical asymptote. So something like this. And what happens is you'll see one of the lines will bend like that, and the other one will bend like this. And you see the way they can't have this y value here. It's like an invisible barrier. That means that not every what's that word? Not every y value can be used. Hence, bunks it back to injective. Yes.
So what would be surjective?
Standard curvy function. Because the horizontal lines hit the graph more than once, it's automatically surjective.
And bijective would just be
Perfect one-to-one, a straight line.
Okay.
Everything's busy and everything has a one-to-one correspondence. Cool. Okay. Now, next one. You may think this one's really hard, but it's actually quite easy. So, what we have is write down the antiderivatives of the following. Shh. Listening. Guys, integrate it. So when we integrate this, it's going to be a quarter x to the 4, right? You add 1 onto the power, then add 1 onto the power here, it's going to be minus x cubed, because You differentiate x cubed, you get 3x squared. When you differentiate 3x, you get 3. Now, great thing here is that's an answer. If I differentiate this one, because any constant disappears, I can put any number I want here, and it will automatically, when you differentiate it, it will automatically get rid of the last number, and hence just leave you with this part here when you differentiate it. So any number at the end will do. Okay.
I don't know what you did there. That looked close.
I integrated it. An antiderivative means integration. I integrated it. Okay. And do you remember? See, technically, I'm integrating a integral that has no indefinite integrals. Exactly what it's called. I'm integrating an indefinite integral. Okay. So there's going to be a c value at the end, and I'm just making up my own c values.
That's all you have to do.
Yeah, make up your own c values. All right. Cool. What is the indefinite integral of a function? I didn't like the definition of the solution, so I just looked up the internet for it. It's exactly what I thought it was. An integral expressed without limits. So an example. This here is an example of a integral with limits, a definite integral, if you will. And an example of an indefinite integral would be something like that. The only key difference is absolutely no limits. Is that alright? That's why you add on the constant at the end. Now, next part. Write down the indefinite integral of g, the function in part 1. Okay, so the indefinite integral of g. So, what we're going to do is integrate g of x and to respect with dx. And then what we can say is we can integrate, it's our answer from part 1, a quarter x to the 4 plus 3x. Minus x cubed. Minus x cubed. What's after that then? Plus 3x. And I said is any constant I want, wasn't it? So anything we want, c or k, whatever. And then put your dx at the end. Okay. Now, that's all done. What we're going to do next is a very important one. If you guys aren't used to these ones, I have a video where we do lots of these ones. These ones unfortunately weren't in your concise maths book, so they're very important. Shh, lads. Excuse me. What'd you say? The second question was in your concise maths book, right? Before Christmas test, before the summer test last year, very last 2 weeks, I went over these and gave you several examples and linked you to the video before the test. Okay? I'm just reminding you of this and this video again. So, what we have is differentiate this. U and V. Differentiate. Okay, so it's the product rule. So du dx is, u is 1, or so u is x, du dx is 1. Phi is ln x, the v dx therefore is 1 over x. Differentiate. First derivative therefore is phi times du dx plus u times the v dx, which is going to get me, let me see, phi times du dx. 1 times ln x, yeah. After that, plus u times x times 1 over x, and what that's going to get me is ln x plus 1. Now, yeah.
If there was like a number, it was like.
Guys, now, the trick is with this one is how do you integrate ln x dx? We've never done anything like that before, but it says the word hence. Okay, the word hence is what we're looking to exploit here. Y equals x ln x. Everybody happy with that?
Yeah.
We differentiated it earlier, and when we did the derivative, we got what was it, 1 plus ln x, or ln x plus 1. After that, what I'm going to suggest is we do this. We cross multiply, and we say that dy equals 1 plus ln x dx. Everybody happy with that? Okay. Once you're done doing that, what we're going to do next is we're going to sort of break this up a little. We're going to use the dx on both parts separately. So we're going to get dy equals 1 dx plus ln x dx. Okay? Right. what it did was, I see the way I did dy dx as a fraction. I cross multiplied that. The dx is being multiplied to 1 and the ln x. I multiplied it out to get ln x dx and 1 dx. And now I have dy here. The next thing I'm going to do is I'm going to re-look at my question. I want the integral of that. So I'm going to integrate this one, this one, this one. Okay? Once I've done that, what we're going to look at next is, okay, what's the integral of dy? The integral of 1 dy. What differentiates and turns into 1? If the letter we were integrating by was dx, you're right, but it's y. When you differentiate y with respect to y, you get 1. In the same way, when you differentiate x to respect to x, you get 1. What's the integral of 1? X. Okay? And then we don't know how to integrate that. That's the whole point of the question. We want to find this thing on its own. Okay? Next thing I'm going to say is that this thing on its own is going to be y minus x. Would you agree with that? So the integral of ln x dx equals y minus x. And then the integral of ln x dx is y minus x. Now what is y? There it is there, isn't it? X ln x minus x. And the one thing we forgot, you know when you integrate and there's no limits, we got to put down a c at the end. That's your answer there. Now, for lads, what we're going to do here is find the value of f of 0.2. It's very simple. You're just going to replace 0.2 in for x. I'm not going to spend too long here. 0.2 squared plus 5 times 0.2 minus 0.98. Put that into the calculator and you're going to get 0. F of 0.2 is 0. Just use your calculator. Okay. Show that f has a local maximum point at 5, 11.52. How would you show it has a local maximum point? Differentiate once and put it equal to 0. When you differentiate that once, what happens? Minus 2 times minus 0.5 minus 1x. Differentiate 5x. 5. Differentiate minus 0.98. 0. X equals 5. Just bring the x out of your side. X equals 5. We're going to replace that 5 back into the original formula. I'm not going to do it because I think we can all do that. Yeah. Replace 5 back into the original formula and you'll get 5, wherever that is, 11.52. It's a no-brainer. Okay. Now that we've done that, what we're going to do next is it's going to ask me to draw this. Okay. So it says a sprinter's velocity over the course of a particular 100-meter race is approximated by the following model, where phi is the velocity in meters per second and t is the time in seconds from the starting signal. So what I'm going to ask one of you guys to do now, guys, okay, it's a typical N-shaped curve, okay, but it gives me some modifications to use. Right here the modifications are, okay. It says first of all from 0 to 0.2 on the t-axis. So this is my velocity axis here, and this is my time axis here, okay. And so that's velocity and that's time. Now what it says is it remains at 0. The output is 0 from 0 to 0.2. Remember we tested f of 0.2 earlier and we got 0? That explains this little region in here. It flatlines at the start. Okay, it goes straight across. Then all of a sudden, it starts to, your sprinter starts to increase his speed. His speed is increasing with time. Okay? Now he reaches a maximum velocity of 11.52. Now 11.52 is we determined that in the last question to be the maximum point. He then hits a maximum velocity. Upon hitting the maximum velocity, the rest of the curve is now irrelevant because he's not going to immediately slow down. He's going to continue going at the same speed. Does that make sense? So he's going no speed up to 0.2. He starts accelerating. His speed gets faster over time, and then eventually he reaches his maximum velocity 11.52 and then goes straight across for the rest of the race until for any time greater than 5 seconds. So the black part has no significance on the graph. Okay. Now that's the sketch of the graph. For the first 7 seconds of the race, you'd stop around where's 7 seconds? So you'd stop. Technically speaking, we're stopping. Oh dear. We're stopping, nope, don't want that. 7 seconds, so we're stopping here. Okay, so we're stopping up there. Now, what's the next question is going to ask me after that? Find the distance covered by the sprinter in the first 5 seconds of the race. The distance. Now, that's an interesting one. Anybody know what the distance is?
Speed by chance.
Now, alright, in a velocity time graph, guys, the integral is the distance. So you want to find this here. See this here? This shaded region? That is that's going to be your integral of 5 to 0. And what's our function? Minus 0.5 t squared plus 5t minus 0.98 is going to be dt or dx?
So how can be to 0? This is a flat line to start with.
Oh, 0.2. Yeah. I think the 0 wouldn't really make a difference because there's no area anyway, because it is a flat line, but yeah, 0.2, you're right. So, because 0.2, you're right, 0.2 is the start of the curve, okay? So, and it's dt here, isn't it? Not dx. So you integrate this, okay, I'll just integrate it down here. And what we're going to get is t cubed, isn't it? So it's going to be minus 0.5 over 3t cubed. The next one is going to be t squared, and it's going to be 5 over 2t squared because you're going to multiply by 2, and that's going to be the division by 2 when you differentiate. And then the last one, we just got to put t at the end, 0.98t. That is from 5 to 0.2. I'm trusting you can take care of this part of it, just putting the limits and taking them away, hoping you're at that stage. So what we're going to get is 36.864 meters. Okay. After that, done. Find the sprinter's finishing time for the race. Give your answer correct to 2 decimal places. So, alright. Find the distance travelled by the first 5 seconds of the race. We agreed that that was 36.864, yeah? Now, I need to... Now, is he running a 100-metre race or what's he running? It's a 100-metre race, okay? So, 100 metres, take away our 36.864 is...
The speed before he reaches maximum.
No, that's the distance he's covered.
Before he reaches the maximum.
Yeah, distance before he reaches his maximum speed. So, we're going to take that away. What do we get? I think I have it here. 63.136 meters, okay? Now, when we've covered our 36 meters, we're at this peak here, yeah? And what we have to do is we have to find out what is the distance he travels after he reaches, how fast does he do it? So we know that he's traveling 11.52. So it's going to be distance over time. So distance over time, distance over speed equals time. And it's going to be 63.136, and you're going to divide that by the speed of what? And we're going to get 5.48 seconds. Okay? And then we have to add that onto the original 5, because, and then we get 10.48. Okay? Okay, so 10.58 seconds. Okay? Now we're on 9C. Now 9C would have been done in, once again, there's a full exercise in this in your book, but it's been a while, so you might not be familiar with these, okay? So a spherical snowball, so sometimes it just helps to just draw the thing out, and it goes, it's melting at a rate proportional to its surface area. That is, the rate at which its volume is decreasing at any instant is proportional to its surface area at that instant. Prove that the radius of a snowball is decreasing at a constant rate. Now, if you're looking just for marks here, just write down volume of a sphere, forward 3 pi r cubed, surface area of a sphere, 4 pi r squared. So you understand that that's... What? Yeah. You might get a bit low partial credit for that. Like, that's about what you can do in anything, okay? Now, what it says is that your volume is reducing over time. When a snowball melts, you would agree that its volume is reducing over time. It's decreasing, yeah? Decreasing means a negative slope, which means a negative number. Okay? It's proportional. If something's proportional to something, if I said my height is proportional, what's the proportional sign again? I think it's that, isn't it?
Yeah.
To weight. My height is equal to a constant times my weight. It means it goes down by the same factor each time. So we're going to put in a k here. K just to represent the proportionality constant, okay? So k times surface area, A. Therefore, the v dt, now we're going to we'll actually just do one step at a time and replace A with 4 pi r cubed, so minus 4k pi r squared. Now, what it says for me to do here is to replace in the v. Okay, so I'm going to take out the v and I'm going to say it's the derivative of what is volume of a snowball? Oh, sorry, volume of a 4/3 pi r cubed. Okay, so let's differentiate this. Okay, now the problem there is, okay, what's differentiable in this bracket? Constants don't need to be differentiated, do they? If we differentiate 3x, what do we get? 3. If we differentiate 3r squared even, it's the r squared that's the differentiable part. Whatever our answer is, we're going to multiply it by 3. Okay? So what we're going to do is we're going to treat the 4 over 3 pi as a constant. So what we're going to do is we're going to take it on, we're going to remove it to the outside. 4 over 3 pi, and then it's going to be the d dt of r cubed equals minus 4k pi r squared. Now, sorry?
So you're only here differentiating
Differentiating the r cubed. Now, the problem is we're differentiating the r to respect of a different letter. Okay? So how this is done is you differentiate the r cubed as normal, and it will be 3r squared, yeah? And then, because you can't differentiate r with respect to a different letter, you leave it as dr dt. You want to differentiate the radius with respect to time, okay? And then that's 4k pi r squared. Now, if you look at both sides, the pi r squareds are going to cancel, aren't they? The 3's are going to cancel. And you're just going to be left with dr dt is minus 4k. Now, I'm hoping that's it anyway. Oh, the 4 is going as well. Where did I leave the 4? Oh, there's a 4 there as well, wasn't there? So the 4's will cancel. Yeah, Connor?
I get everything except for that second step in red there.
Alright, go on. What we had to do there was implicit differentiation. Implicit differentiation no longer on the course, hence this question is no longer applicable.